Welcome back. We'll continue with our study of the constitutive relations of linearized elasticity. What we've seen so far is the fact that our elasticity tensor C is symmetric, right? It has major and minor symmetries. We saw what these mean and why they hold. Continuing, right. In the context of linearized elasticity, there is a another very important property that C holds. Okay, so C is positive definite. Okay, and here is what we mean by saying it's positive definite. For all tensors, and I'm thinking of what I should use as a general tensor here. Let me use theta. Okay, I hope that doesn't disturb any of you too much if you're used to seeing theta as temperature or angle or something. Anyway, theta is a tensor for me. So theta is a general tensor, so it doesn't need to be symmetric, so I'm going to say it belongs to that space. That's not a notation I've used before. GL3 simply means the group of general linear, I guess I should capitalize them, right? So, okay. General linear transformations in R3. Okay, that's what GL3 is. It's just a fancy way of saying matrices in 3D, if you choose to look at every tensor as being a square matrix. Okay, anyway, so supposing we have this, right? Then what we're saying is that for all theta belonging to the space, we have the following result. Theta contracted with C contracted with theta again, right? So we form this quadratic product of C with theta. Okay, this is greater than or equal to 0, right? The scalar for all theta. Okay, in coordinate notation, this is what it means: theta ij, Cij kl, theta kl is greater than or equal to 0. Okay, that's what we're saying. It's useful to write this in coordinate notation just to be sure that this quadratic product is indeed a scalar. Okay, so it's greater than the real number 0. Okay, this holds for all theta belonging to GL3. In fact, what we can also show is that actually the equality, right? So theta contracted with C contracted with theta equal to 0, right? Which is one of the cases of the inequality on the previous line. This special case, the equality holds if and only if, IFF to mean if and only if, theta itself is the 0 tensor. Okay? Right? This is the condition that holds. Okay? Now, this is very important in the context of linearized elasticity. It essentially translates to the condition that linearized elasticity talks about materials that are fundamentally not subject to material instabilities. Okay, and this is important if you can imagine, as you may imagine, if you're going to compute with this model, right? We're going to put stresses and strains, we're going to put loads on it. It's important to know that material instabilities within the context of linearized elasticity are inadmissible. Okay, so what this means is that linearized elasticity theory has no material instabilities. Okay, if you're wondering what a material instability could possibly be, fracture is a material instability. That's not covered by linearized elasticity. Okay, you need to do special things beyond linearized elasticity to admit fracture. Likewise, slip bands or shear bands, which form in the context of extreme plastic deformation, are not covered by linearized elasticity. Well, you have to include plasticity theory for that. Okay, so that's all this is saying. It's important, however. It's actually very important, and we're going to see another result which which brings out that importance. Okay, what I'm going to do next is actually give you a very special form of the elasticity tensor, but one that is used very widely. Okay, so we are going to look at we're going to write out C for materials that are isotropic. For isotropic materials. Okay, of course, this is for isotropic materials, long as we want to treat them with linearized elasticity. And of course, we're talking mechanical isotropy, right? Okay. Right, let me first write it in coordinate notation. Okay. In the context of linearized elasticity, the requirement of material isotropy also translates to the fact, and this can be proven, that the material can be entirely specified elastically with just two constants. All right, and those constants are what go into C. So, with that being stated, here is what C looks like for an isotropic material. Okay. One of those constants is lambda. I'm going to denote it as lambda. So,Cijkl is lambda times delta ij delta kl, where can you guess what the delta ij refers to? Kronecker deltas. Right, and of course this one too. Okay, so we have that plus 2 mu times 1/2 delta ik delta jl plus delta il delta jk. All right. If you wonder why I put in a 2 mu and then reintroduce the half, it is because what I have here is also often recognized as a fourth order tensor. Okay, this is often denoted as sort of a bold-faced I with indices ij, kl. Okay, and this is what we call the fourth order symmetric identity tensor. Okay, what it does is the following. if you take I as defined there, okay, and feed to it any second order tensor, right? So let's use theta, which we used in the previous slide, right? And remember, theta is just any old second order tensor. It doesn't need to be symmetric or anything, right? It turns out that I acting on theta spits back for us theta, but the symmetric part of theta, all right, which is, since I'm using coordinate notation, that is properly written as 1/2 theta ij plus theta ji. Okay, so it sort of gives us back theta, but the symmetric part of it, right? So if theta were already symmetric, well, it would just give us back the same tensor. However, in general, when we feed it a non-symmetric tensor, this identity gives us back just the symmetric part of that tensor. Okay. All right. Right. Now, in writing direct notation, so I'm going to use this I in writing the direct notation version of this relation. In writing the direct version notation of this relation, delta ij, the Kronecker delta, I like to write as what I call a bold-faced 1, indices ij. Okay? If you come from the world of matrices, that's just your 3x3 identity matrix. Okay? All right. So direct notation for the same relation is the following. C equals lambda 1 dyadic 1, okay, that's the dyadic product. Okay, and to know what it is, well, just look at the direct notation. That's what it means. Okay, I often call this the tensor product, plus 2 mu times the fourth order identity, symmetric identity. Okay, note that because each of these tensors, each of these ones is a second order tensor, their dyadic or their tensor product gives us a fourth order tensor. Okay, so this is direct notation. All right, what about these constants? Lambda and mu are what are called Lumi constants. Okay, and if they seem unfamiliar to you, they will become familiar in just a few seconds. And here's how they're related, right? If now you use something that you may be more familiar with, if E is the Young's modulus, and if nu is the Poisson ratio. Okay, then the relations are the following. The Lumi constants can be related to these guys. So lambda is E nu over 1 plus nu times 1 minus 2 nu. Okay, and mu is E divided by twice of 1 plus nu. Okay, chances are the Young's modulus and Poisson ratio are something that you've encountered almost certainly in your second year of your study of mechanics or engineering or something like that. Do you recognize what this is? Do you recognize what mu, as defined as that, also gives you? That should be a little more familiar if you recall these sorts of relations. It is the shear modulus, right? All, of course, for isotropic materials. Okay? Lambda is not something that's related to shear or anything. It's just often just called the bulk, a Lumi parameter. Yet another modulus that you may be familiar with is kappa, which is the bulk modulus. right? So kappa is related again to E and nu as E divided by 3 times 1 minus 2 nu. Okay? All right. So there are limits on these constants, and I'll talk about them in just a bit. It emerges that nu can lie between -1 and half. All right, for the linearized theory of elasticity. Okay? Do you recall what this limit corresponds to? No? This corresponds to elastic incompressibility. Okay? And as you may imagine from here, if you approach the limit nu equals -1, you get a material that is shear unstable, right? So actually, well, actually to use this theory properly, I guess let's just do that, okay? All right, because otherwise linearized elasticity tends to break down in those limits. So let's just leave those actual limits out, okay? All right. Also from here you may be able to see why nu equals half is the limit of incompressibility, because it makes the bulk modulus get unbounded. Okay, so you have a material that's very, very stiff to compression, right, like that. Okay, fine. So let's get back to talking about positive definiteness, right? So having put down this form of the elasticity tensor for an isotropic material, the condition of positive definiteness okay, it translates to a requirement on our on the elastic constants that we were working with on the previous slide. Okay, in particular, one can demonstrate the following. Positive definiteness implies the following conditions. It implies that lambda plus 2 mu has to be greater than 0. Okay, it also implies that mu itself has to be greater than 0. Okay, if you come from the world of structural dynamics or acoustics in elastic materials, these conditions may mean something to you. Okay, can you recall it? No? Okay, well, let me see, or maybe some of you do know. Well, the reason these are important conditions is the following. In elastic materials, waves propagate in at least 2 ways in the bulk of a material, as longitudinal or shear waves. It emerges that the longitudinal wave speed is lambda plus, sorry, that lambda looks bad. The longitudinal wave speed is lambda plus 2 mu divided by the mass density under the square root. Okay? So when we say that lambda plus 2 mu is greater than 0, what we're saying is that we have real wave speeds. It allows longitudinal waves to actually propagate through the material. Okay? And the shear wave speed is square root of mu divided by rho. Okay? So these conditions on lambda plus 2 mu and mu essentially allow us to have propagating longitudinal and shear waves. In the elastic material. In the elastic material that we are describing with this linearized theory of elasticity. Okay. Let me see now. Now, it turns out that in most materials of interest, the longitudinal wave speed is greater than the shear wave speed. Okay, and that's a fact that is sometimes used in geophysics too, when people are dealing with earthquakes. Anyway, all right. That is probably the basic material we need to know about our constitutive relations for elasticity, for linearized elasticity. And there is more, of course, that can be said, but it's not. But we don't really need to get into it, I think. Okay, so we're going to end the segment here. When we return, we will work with the weak form.